So you heard about the plan from Gail, and I would like to invite our first PI, David Moore, to come up.
I think your screen share is paused. I don't know if you can. Kristen and everyone for helping to organize this. So in our group, we're actually connecting to a couple of the things Gail talked about. We heard the highest priority for new construction experiments. Very carefully crafted sentence involves neutrino double beta decay. I will tell you about all the great discovery potential because Gail did that, but I will say that there were 3 experiments specifically highlighted there: Cupid, Legend, and Nexo. We'll hear about Cupid in a second, but in our group we work on Nexo, which is a 5-ton liquid xenon time projection chamber aiming to search for this decay with a half-life up to 10 to the 28 years. So a factor of 100 really in sensitivity for this isotope over the existing experiments. We think there's a lot of discovery potential as we go 2 orders of magnitude. Our group at Yale has scientific leadership for building this photon detector, which is 4.5 square meters of UV sensitive silicon photomultipliers to be able to image the light that comes out of the xenon when one of these decays happens. And we're closely collaborating with the B&L instrumentation division. This is actually just by itself a pretty advanced and new technology for reading out the scintillation light in such a detector. So we're quite excited about that. And for Nexo, we're at the conceptual design stage. We actually just had this conceptual design for this photo detector reviewed a couple of weeks ago at B&L. We're hoping to get to CD1 and starting to push forward on the project on whatever budgetary scenario is possible coming soon. The other thing we're quite interested in is actually one of the strategic opportunities Gail mentioned. So she talked about, fundamental physics, including neutrino mass and precision measurements of beta decay, which still allow us to learn lots about new physics and neutrinos in general. And in particular, we're interested in applying quantum sensors to problems in nuclear physics. So our acronym for this is QUIPS, Quantum Invisible Particle Search. But the idea is to take these 100 nanometer diameter particles that we trap in our lab, implant beta emitters, and then we can actually, by measuring these things at the Heisenberg limit, essentially at the limit dictated by Heisenberg in our measurement process itself, hopefully we can measure the momentum of a single neutrino leaving a tiny glass nanoparticle at the, with high signal to noise, and search for sterile neutrinos, test the kinematics of that decay. So we're quite excited about this. I think this is really an emerging opportunity, and it's highlighted in the report that new precise sensors might also help advance nuclear physics. So, thank you.
We go on along the theme, I think, of double beta decay.
Okay. So this program also at Yale contains the Core double beta decay search, and Carson will talk about Cupid next. So this we are running and taking data, and so with this we are contributing to, we're part of the recommendation, and but in particular, I wanted to just highlight the recommendation 1, which is the highest priority of the community to capitalize on the extraordinary opportunities for scientific discovery made possible by the investments in the US. So with Core, we're looking for neutrino double beta decay in tellurium-130. So tellurium-130 with a Q value of 2.5 MeV. We're using a technique called cryogenic bolometers. With this, we have tellurium oxide crystals that are cooled down to 10-ish millikelvin. And when there's a particle interaction with the tellurium oxide crystal, then that results in phonons or heat that is produced with this interaction. And so our group, so I was in charge of creating the NGD thermistors, and this is all implemented into this big, huge cryogenic bolometer sector here, shown here. So I'm currently the co-spokesperson for the US co-spokesperson for the Core experiment collaboration. And I wanted to just introduce the group here. You're going to all raise your hand when you're, those of you working on Core. And we've had students also, students and postdocs that graduate to university physicians, car max, car salesmen, doing data science, also doing things like self-driving cars, telling us what TV programs are effective. Yeah, so just national labs. So we're just having focus on certificate.
Great. So I will briefly talk about the future of double beta DBK with bolometers. This is Cupid that builds on the experience that we have with bolometers in core, uses similar techniques, different isotopes, and this connects to recommendation number 2. As you heard, the highest priority for new experiment construction is a program or an international consortium of neutrino-less double beta decay experiments with different isotopes and techniques. So Wright Lab and Yale are involved in multiple efforts, as you heard. There's an EXO, most likely to be located at Snow Lab in Canada, the deepest underground lab that we have in the world. And then Core and Cupid are located at the Gran Sasso underground lab in Italy. And what we are planning to do for Cupid is to use the same approach as Core. We build big bolometers, but not out of tellurium-130. We want to use molybdenum-100. This gives us a different Q value, which is higher. So we reduce the gamma background. And in addition to the thermal sensors that Reina worked on, we want to add light detectors. So we get better discrimination of alpha and gamma backgrounds, ultimately reducing the background to the experiment. The name of the game for double beta decay is to search for an extremely rare process, hopefully observe a handful of events over essentially zero background or something that's very low. And so this is one approach that we are pursuing. And I have to say that I'm very excited that here at the lab, we can actually carry out a program with an EXO, Core and Cupid that has different approaches, multiple techniques. And hopefully one of us will see or actually both. One of us sees them and the other not, then we have a problem. So let me just, along the line of neutrino experiments, also talk about another effort that's happening here. And this is Project 8, a new approach to measuring neutrino mass. This connects to recommendation number 4, capitalizing on unique ways and making strategic investments. And as Gail said on Wednesday, recommendation number 4 is targeted to support projects that lay the foundation for future discovery or the discovery of tomorrow. And Project 8 is a new way to measure neutrino mass. It uses cyclotron radiation emission spectroscopy. We essentially use tritium in a magnetic field, and then we look for the radiation from the spiraling electron. And we just recently published the first results from the prototype experiments. This is actually a real tritium spectrum measured with this techniques, and we have used it to set a limit on the neutrino mass at 155 eV, not quite competitive yet, but it's a potential way to surpass Catherine and the current limits on neutrino mass with a future scaled up version of the experiment. So we're excited with this recommendation to be able to scale this up, and we will be building the next version of the prototype experiment here at Wright Lab. And as you heard at the beginning, the people, our students, postdocs are the key to making this a success. Big shout out to them. And they are the ones who actually do all the development work. So with this, I'd like to hand it over to the next topic.
Okay, so we, Helen, John, and I came together to put together our thoughts on the long range plan. So we do have 3 slides, but there are 3 of us. So we're the relativistic heavy ion group here at Yale. And just kind of to start talking about the group. So along with recommendation 2, recommendation number 1, they stated that the highest priority was including expanding policy resources to ensure a safe and respectful working environment for everyone in order to realize the full potential of the nuclear workforce. And so on that lines, we have a very large nuclear workforce within our group. And so maybe like separated and maybe everyone in the relativistic heavy group that's here could raise their hands. And yeah, we have somewhere like 10 on average, 10 students and postdocs, our students and undergrads in the group at a time, and a few postdocs as well. And within our group, we really believe that promoting a safe, equitable, inclusive workplace will increase excellence in science, which is kind of along with the statement from the long-range plan. Yeah, so just wanted to give you a quick snapshot of some recent activity. So on the left is showing graduate students in our group presenting their results at international conferences. You can see Sierra, Andrew, and Yachi. And then on the right is showing some undergrads and graduate students working with the new research scientist Prakar in our group on detector R&D for the EIC, which was not in the plans. Yeah, so here in the relative heavy ion group, we have work ongoing both in hot and cold QCD. So starting with hot QCD, so one of the visions talked about within the long range plan was to build on the ongoing world leading US program, which includes exploring the nature of curriculum matter at both BRIC and with the heavy ion program at the LHC. And so over the next kind of few years, RIC will complete its science program with both SPHENIX and with the upgraded STAR. And then as RIC transitions to the EIC, the LHC program will lead the hot QCD physics. And so yeah, so along these lines here in relative heavy ion group, we have a complementary program where we're involved on both the ALICE experiment at the LHC and the STAR experiment at RIC. And here we're trying to answer this question. We're trying to understand the properties and dynamics of the curriculum concept. And so within our group, we have we're involved in collaboration leadership, and we're involved with the ALICE TBC and STAR for upgrades and commissioning. And within our group, we of course are very involved in analysis, where we focus on things like jets and jet substructure and particle yields and fluctuations in the bulk. And so as an example, one of the things that was highlighted in this section of the plan was using jets to study the space-time structure of the curriculum plasma. And it was also highlighted as a feature probe of QCD at the EIC. So now the last component. And so, like I said, we also have a involvement on the cold QCD side, where if you were listening to Gail, she was talking about how one of the third recommendations was the completion of the EIC as the highest priority facility construction. Yeah, and so here within our group, we have a rapidly growing R&D program for construction for the EPIC detector at the EIC, where we have a few ongoing projects, including characterizing photosensors for sharing cloud detectors, characterizing symptoms and tiles for hadronic calorimeters, also R&D for gaseous detectors for tracking, and some new projects on CO2 cool.
Great, thank you. And as we heard in the plan, not only experiment and facilities are important, but also theory. And also wanted to invite Yoram to say a few words about the current nuclear theory effort and how it connects to the long-range plan.
Yeah, I'd be happy to do that. So I discuss very briefly the connection of the local nuclear theory effort with the long-range plan. So our research program is very broad, and it contains several topics in nuclear theory in related areas. I will discuss mostly two topics related to the long-range plan. The first one is nuclear many-body theory, and the second one is called atomic gases, in particular Fermi gases. So if you read the report, the whole report is very, very long. Chapter 7 discusses theory. So I thought I will cite the relevant section to our research. So the first topic of nuclear many-body theory is tied well to section 7.1, or the foundation for theory research. So as you know, in nuclear theory, one of the main challenges is to derive nuclear properties from the underlying interaction between proton and neutron. In particular, there's a lot of interest in what are called statistical properties, because they're important input for nuclear astrophysics processes, for example, nucleosynthesis, the Hart process, supernova, and so on. These properties play a really key role. More generally, they are relevant for statistical nuclear reaction, and often the rate of this reaction, including in the Hart process, are not well being measured. So the theory really played an important component in this effort to understand, the Hart process. Another interesting topic we are studying in the group is under the title of thermal and quantum phase transition in finite size system. And here is an example where it's hard to see the levels here, but this is an example of a quantum phase transition from a spherical shape to the formed shape. This diagram, depicts, the different shape of the nucleus. So only adding 2 neutrons, you already make this kind of phase shape phase transition. Now, if you go to finite excitation energy, means finite temperature, you again become spherical. So this is again very interesting, especially because usually finite size system, you don't strictly have phase transition, but you can see the signature of the phase transition that happen in this kind of system. Now, in order to be able to do all these studies, we have developed state-of-the-art quantum Monte Carlo method for nuclei which work in Fock space. So the main idea that in this method you can actually solve in model spaces that are many orders of magnitude bigger than what you can do in conventional method. So it's a very powerful method, this quantum Monte Carlo method. Second topic that we discussed in relation to the long-range plane are called atomic quantum gases. This is section 7.3 in the report, which is titled Connecting Across Field and Disciplines. In particular, they mention, the cold atom topic, and this is interesting to many disciplines, ultra-cold fermions. The reason is because it's a clean paradigm of strongly interacting Fermi system. So you have strong interaction, but the interaction is very clean, it exactly, and the experiments can actually measure it. And we've done quite a bit of work in this direction. One interesting thing that happened in this system, you have a crossover from Bose-Einstein condensate to Bardeen-Kuber-Schrieffer. And you can see it in the fermionic system. And another, in between the two, in the crossover, is something called the unitary gas. Okay? This corresponds to the strongest possible interaction. So it's a highly non-perturbative system. And actually, this is very interesting in many disciplines because it has connection to neutron stars, to nuclear astrophysics, connection to covalent plasma, so into CD, and in condensed matter to ITC superconductivity. And again, we have developed in this context a lattice Monte Carlo method. So we generalize the method done in Fock space to the lattice. And in fact, this method turned out to be the most accurate among a whole bunch of strong coupling theories. So many of the strong coupling theories are based on uncontrolled approximation, where the Monte Carlo is controlled up to statistical errors. So it's very accurate. And we do it on the lattice, so it means there's a finite spacing. But in the experiment, you have the continuum. So the continuum limit is very challenging, and here's the diagram showing schematically how this is done, but in practice, it's a very challenging thing that we're able to do. So I will mention that to do all of this thing, high-performance computing was very crucial in what we've been doing. And in fact, I cited a sentence from the long-range plan. Advanced computing has been identified as a strategic opportunity, which we discussed in chapter 1. So now we're going to this what's called exascale computing, and this is very exciting period. You can actually solve problem that you cannot think about solving just a decade ago. So.
Thanks so much, Yoram. Before we close, the session and the presentations here, just wanted to remind everyone, November 8th will be the Nuclear Physics Day on Capitol Hill. As you heard from Gail, this is going to be organized. We will be reaching out to people to participate, talk to your PI if you're interested in spreading the word about this new long-range plan. There will be the joint APS-DNP fall meeting, which was rescheduled. It's now happening the week after Thanksgiving. There will also be a special presentation and session on the long-range plan at that meeting. And so there will be activities to get the word out and talk about things. Just in closing, I wanted to say that I'm really excited to see how many local efforts here are part of the scientific effort that have been identified as high priority for the next decade. It's exciting to see. I think it's exciting to see what we are doing will get priority over the next decade. It's important for the future of the lab. And also that workforce is recognized, and all of you play a role in building the nuclear science community, building an inclusive community, and this is going to be a priority for the future. Before we head to the photo, I wanted to give Helen perhaps the last word to close this, and then we will perhaps all assemble in the atrium and take a group photo.
Yeah, so thank you everybody for coming. It really is good to see how large our community is here at Wright Lab. And if you have questions, we are all around. If you have comments, if you want to find out more, please come and find out any of us. We're happy to talk, as you know. And let's go and take our photo. Thank you.